This meeting is being recorded.
So, welcome to today's seminar. Our today's speaker is Grzegorz Lisowski. He is our visitor from AGH Krakow, and he will talk about discovering contiguously elections.
So, hello everybody. So, first of all, let me thank you for having me here. I'm having a great time and making progress. So, I'm very happy that I had a chance to be here and to talk to you about some of our recent research. So, today I'm going to talk about work which is also going to be presented AMAS this May, in case anyone is going. And work that I've done with Łukasz and Stanisław, also from AGH, and with Jérôme from Paris Défense. So this is going to be a social choice talk, but it's going to be a bit of a different social choice talk. So I'm not going to talk about voting, even though I'm going to talk about elections, but rather I'm going to speak about things that we can learn from elections, not necessarily selecting a winner. So we can think about elections, which are essentially a bunch of rankings over candidates, as kind of an information about what people think, or about views of diverse preferences that the society might have. So it is usually used to select a winner or to choose the best option when people have different views. But actually, we can learn something about the structure of the society, because we can think about different groups who think in a different way. And studying this aspect of elections is precisely what we tried to do. Namely, the goal of our study was to learn about specific groups in the society, knowing only their preferences over certain items. So, for example, you can imagine somebody, say, we have aliens coming to Earth from outer space, and they have no idea about humans. They just see some things that they learned about people, and in particular, they can notice that some people prefer beef to chicken to fish to tofu, but some other people absolutely hate chicken, lamb, beef, or whatever, but they love vegetables and they love tofu or whatnot. And then they don't know what a vegetarian is. But then looking at these preferences, they can detect that there is a group who thinks like that, and who, like if we put a name on it, is vegetarians. So we would like to learn something about how to detect such groups. Is it possible computationally? And if we can actually detect them in practice. So let me talk to you about the model that we considered. So an election is defined just as a tuple of preference orderings over some set of candidates. So here we have, okay, it doesn't work. We have 6 voters and lovely candidates, namely a penguin, a sheep, a mouse, an owl, an elephant, and a squirrel. So that's a very simple mathematical object. And what we want to consider is subelections. So we would like to restrict our big elections to some subset C prime of candidates and a subset B prime of voters. So we have this huge matrix, but perhaps we are only interested in some 3 candidates and 3 voters, so we can find this submatrix. So we will be considering not only one type of consistency, because consistency can be understood in many different ways. But the first type of consistency is what is known as clones. And we say that 2 voters are clones with respect to some set of candidates if they rank them in a single interval. Namely, perhaps they have different preferences about these candidates, but they kind of rank them next to each other. The question in this sublection is whether we can find such a clone structure with 5 voters and 3 candidates. So I'll give you 20 seconds and then I'll ask for a show of hands. Okay, so who thinks that there is such a subset? Who thinks there is not? There is one. So if we take a look at a penguin, a sheep, and a mouse, then we can notice that for voter 1, 2, 3, 4, 5, even though they vote them in different orders and these triples are in different parts of their preference orderings, they are always next to each other. So for the computational problem, we're just asking for a given 2 numbers, n prime and prime, whether such a structure exists in the election for n prime voters and n prime candidates. So computationally, it's perhaps not very difficult to prove that this problem is p-time, because if you take the number of candidates, a single number, you can, in polynomial time, check for every voter every segment of length m, and then we can choose the most popular such segment among each voters, and then we can iterate for every m until we found a good solution, or we concluded that such a solution does not exist. So that was relatively easy, but things will be a bit different when we consider perhaps the most natural kind of consistency, namely identity. So for identity, we're just looking for a sub-election in which all voters have the same rankings. So a similar question as before. So in these elections, can we find an identity sub-election with 3 voters and 4 candidates? Who thinks yes? Who thinks no? Yes. We found 3 voters who rank a penguin, a sheep, a coal, and a squirrel in the same ordering. So for these numbers, the answer is positive. So we define the computational problem in a symmetric way. So for a given instance, we check if there is a sub-election of a given size that is an identity. So here the problem is not that simple. It is NP complete. So I'll give you an intuition for a reduction from simple 3-set. So let me take my 3CNF formula and construct the following elections. So first, for every variable, I will construct 2 literal candidates, xi and not xi. And I will create what I call main voters. So these main voters rank literal candidates in the order of the variables, so from x1 to xn, but there will be 2 of them. And they will differ on the rankings of positive, negative literals within every variable. And moreover, to account for satisfying clauses, for every clause, I will consider 3 candidates corresponding to particular literals. And these closed voters will ensure that if we select a literal which witnesses satisfiability of this clause, then this literal really will be selected. So the way it's all going to work is that we're going to seek exactly X candidates. So we can already see that for the construction of main voters, it will force us to choose exactly one of the positive or a negative literal, because otherwise there will be a clash. I will require for every class to select one close voter, and the way in which the consistency will be ensured is that, for instance, for the literal xi, I'm going to push the negation of this literal behind the segment for x2 and not x2. So now we will obtain that every solution encodes a valuation. I will ensure that if I select xi and this closed voter, then there will be a consistency, otherwise there will be not. So for example, I selected x1 and everything is fine, but if I would select this closed voter and negation of xi, I would break the consistency. And like introducing some more variables to make sure that every clause selects exactly one clause voter, we will obtain that there is an identity of our size exactly when phi is satisfied. So that was general NP-hardness, but we get some tractability. So the first observation is that if I fix a set of voters or of candidates, then the problem will be polynomial time solvable. So it will be polynomial time to check whether I can select candidates for these voters such that the problem holds, and it requires a bit of tricks. So if we fix a set of voters, we can introduce what we call the unanimity graph on the set of candidates. So have an edge from C to C prime. If all of the voters in the set agree about the ranking of CC prime. And then noticing that this graph forms a DAG, we can in polynomial time find the longest path in this graph. And for the set of candidates, we just traverse all the voters' orders, and that's relatively simple. And as a consequence, we get an FPT algorithm for the parameters of either voters or candidates in a target solution. So that was about the identity. There is one more type of consistency that we considered, and this is antagonism. So antagonism means that we have a set of candidates that splits the society in half. So we can split the set of voters into two parts. One of them has one order, and the other has the reverse order. So for sanity checks, let me ask you again, in this particular election, is there an antagonism with 6 voters and 3 candidates? Who thinks yes? Who thinks no? Yes. So, I've chosen 3 candidates: an owl, an elephant, and a squirrel. And we can notice that voter 1, 4, and 6 has this particular ordering, and the other has first squirrel, then elephant, and then an owl. So, as before, the computational problem is simply to check if we can find a subelection of a given size, which is an antagonism. So for the complexity, perhaps unsurprisingly, we get NP-completeness, and the proof works very similarly to what we did before, but in this case, essentially, you need to consider main voters that one has a ranking following the ordering of the clauses, and the other reverses the ordering of the variables, and will be essentially fine. So for tractability, I will not be going into proofs, but we get symmetric results. So a p-time algorithm for fixed sets of voters or candidates, and FPT for numbers of voters or candidates in the target solution. Okay, so we've learned a bunch of things about computing in theory, the sets of consistent candidates and voters, but we've learned that on penguins and sheep and squirrels, and perhaps we would like to know something about how the problem behaves in real world. So we have two types of experiments. So one of them is looking at specific types of elections. So can we say something about existence, for instance, of identity in elections that are somehow close to each other? In some sense, I'll get to in a second. And then the second one was to test the real-life data and see what actually happened in the real world with respect to such consistent elections. So first of all, we used what is called a map of elections. So that's a growing framework for experiments in computational social choice. And the idea is relatively simple. So we would like to learn something about elections that are close to each other. So we need to first define what does it mean for them to be close to each other, and in general, like, have some kind of distance measure. So there is a bunch of possible distance measures between a pair of elections. The one that we use in here is the swap distance. So essentially, how many pairwise swaps in particular rankings do we need to make in order to get two copies of elections? And then once we have such a measure, we can plot it on 2D. And in this way, we get a map of elections. So in this graph, every point represents an election, and we have corresponding distances between these dots. And that's kind of a useful tool, because that allows us to think about specific regions in this map. And therefore, we can have kind of a picture what's going on in particular regions of similar points. So in the current data set, we have 344 elections, and each of them has 10 voters and 50 candidates. So let's see what happens. So let's start with identity. So in this experiment, we were looking for maximum identity, so for 5 candidates. So what's the maximum number of voters that we can get for 5 candidates? So the thing we can observe immediately, and that's perhaps not extremely surprising, that if we take a look at identity, then we have a lot of identity. And the further away we go from identity, we have less identity. And indeed, when you compute the person correlation, then we get a very high significance. For clones, clones are interesting because we have very few correlations. So what we can observe is that very little consistency happens around impartial culture. But then we can interpret this lack of consistency as an artifact of the swap distance, because it's enough to make a swap to break clone consistency. So perhaps that means that it might be useful to also compare that with other types of distances. For antagonism, so here again we have looking for type candidates. And we get similar observations to identity, which are again perhaps not extremely surprising, that if you take a look at antagonism, you have a lot of antagonism. If you move down far away from antagonism, then it almost stops to exist. Okay, so now we learned something about these maps and what happens in different regions, but we still don't know much about really realistic settings. So that's why we wanted to check the real-life data. And what's also interesting to us as social choice scientists is whether political election data really differs from different types of preferences, where maybe you can have more of a ground truth, if you will, but it's not exactly sure. So we were again computing maximum consistent sub-elections in different types. And we used two data sets. So first of them was a sushi data set. So for those of you who are away from the field, it's a collection of rankings over 9 types of sushi. So that's definitely not political. And then the other one was definitely political. So it was the data from presidential elections run in 10 of. So let's take a look at identity. So we have these 2 lines. So the blue one is for the sushi dataset, and black is impartial culture. So we generate rankings at random. So you can already see that there is far more consistency in both of these datasets than in impartial culture. If you look closely, you can see that there is a bit more identity in sushi. And a funny observation is that for sushi, rankings actually followed in many times the price tags. So the most expensive were the most popular, which kind of can we see as an argument that there is more ground truth in, say, food types than in political elections. For clones, so first of all, I would like to understand better the clone structures. There is a specific U shape, because if there are no candidates, then obviously clones, and like if there is everybody, then obviously also clones. But we have differences in if you will, how high is this U shape in the bottom. So we can notice that in this figure below for canopy, this U shape is slightly higher than for sushi, and it can be interpreted as candidates having similar affiliations or similar political views, kind of makes them close together in the preferences. And there are also clones in sushi, and interesting One was vegetarian options. So some people hated them, some people loved them, but they were almost indistinguishable for a lot of people. For antagonism, interestingly, in both data sets, there was very little antagonism. So it was very similar to impartial culture. So that may perhaps a little bit surprising. As an interesting fact, the thing that really antagonized people was squid and tuna rolls, for some reason. Okay, so that was about the results that we had. So in conclusion, we studied the possibility of finding consistency in elections in 3 different ways. And for the theoretical part, although finding identities or antagonism is NP-complete, there is in fact quite a bit of tractability results for clones full polytime. We have a few FPT results, so in general, it's not that bad. And we provided an empirical analysis of more realistic instances. So we see this paper as a starting point. So it's more like a start of the journey than the conclusion of the journey. So for this specific paper, there's a number of questions that one might ask. So our definitions of consistency are kind of rigid. So it might be interesting to see what if we relax them a little bit. So we did not really get into restricted domains. So types of elections which might be a little bit more well-behaved. So classic examples of such structures, say, single-picked elections. And we studied ordinal elections, so rankings, but in many cases, we don't have information about the full rankings. Sometimes we have, for instance, approval setting in which you just specify who you like and whom you don't. So it would be interesting to provide such an analysis, but more conceptually, perhaps there is more to learn from elections. Maybe discovering groups is not the only thing that we can learn, but that's up for discussion and that's for a lot of future work. So thanks.
Any questions?
I must have misunderstood because somewhere around slide 15, where you, well, the next one then, I believe. Okay, 2 slides back. Oh, no, it was the 16. Yeah. You have 344 elections, 10 voters each, and 50 candidates.
Yeah.
And then in the next slide, we're trying to find how many candidates satisfy well, the size of the biggest group of candidates with such and such property. How come you can have 50 as the size of the group if you only have 10 voters in an election?
So we have 50 candidates and 10 voters. So we are asking for every dot in this map.
Candidates, not how many voters. Okay,
Yeah.
Sorry.
It's all good?
So I imagine that the experiments you ran, it was the FPT algorithms that you implemented the FPT algorithms that you came up with.
I didn't mention that, but we have ILPs as well.
Okay.
So ILPs were used because I guess they were slightly more efficient.
Any other comments?
It seems somewhat related to like a maximum common subsequence of some strains or something. Can one use algorithms from there or harness from there?
I mean, there was. I think it was. Yeah, we actually thought about that. So yeah, you can. It's not for hardness. It's more for tractability. But yeah, you can use that for sure. Because you're essentially looking for strings, right?
This is permutation, so it's solvable. The general case for n sequences is exactly like you are looking for longest common subsequence and strings, so you can think of that this is a special case because it's
Yeah, but like in principle, yes. The answer is yes.
If there are no more comments, can you speak again?